So far we haven't been speaking about the starting steps of what we are calling the history of deep learning. And basically we have singled out two main milestones in this maybe more development than history. First, we spoke about ImageNet and how that image classification competition changed the perception of what it was possible to do using artificial intelligence in this new flavor called deep learning. We also saw that deep learning could do image classification and also other things, like, for example, our second milestone, AlphaGo, where a deep learning based program, deep learning based software, was able to beat one of the best Go players in the world at Go, something that just a few months earlier was considered impossible, was considered beyond the reach of artificial intelligence technology. We also mentioned briefly that those are not the only two things that deep learning can do or could do back in 2016, and we will speak about other applications in detail in later videos. But now I want to pause a little bit and think about why did that happen, how did that happen, and why did that happen at that moment? How come suddenly these milestones, these huge results in deep learning technology started happening? To do this, I'm going to speak about a confluence of factors, and I'm stealing this idea unashamedly from Jeremy Hopworth, and I will speak about him later, but he is one of the authors of the Fast AI course, which I heartily recommend and will link later. Do check his course because he has lots of things to say about deep learning, and you can learn a lot from that course too. Jeremy Hopworth thinks, and I agree completely, that the reason why all these milestones started happening suddenly was due to several factors happening, coalescing and coming together. What were these factors? Well, the first one are neural networks. You probably have heard about neural networks, and I don't know, neural networks used to sound to me like a new and let's say latest technology type of concept, but they are really not that new. In 1956, as we can see in this picture that Andrei Korenkov has linked in his brief history of AI, 1956, something that could be described as a neural network, or at the very least as the foundation of neural network, the perceptron, was already implemented using hardware at that point, because there were no fancy programming languages then, in one of the first computers, the Mark I. And as you can see, I don't think many people would describe this as the latest in technology nowadays. It was then, it's not now. Artificial neural networks are not new. They are an architecture that tries to mimic or borrow from the way the human brain works. We are going to get into lots of detail into how neural networks operate and how they work, but today I just want to give an intuitive idea about how neural networks in general and deep learning networks specifically work. Basically, we can see a neural network like a function with lots and lots and lots of variables. A function that receives an input and spits out, gives out an output. Okay? Functions do that, don't they? You give them some variables and then they give you an answer, give you an output. Not only that, but we will see them also as a model to solve one problem. What is this model idea? Well, we will have some data, our input, and we will try to solve some problems related to that data, our output. Perhaps the easiest way to think about this is think, for example, about linear regression. In linear regression, we have two variables and we want to fit a model into them. For example, if we consider this very useful Google page from someone called Animesh Agarwal, you have it here. This guy is telling us how to compute a linear regression using Python, but I only want to use this image that he has here at this moment. And basically we have our data represented as quite a few points, and then we want to approximate our data using a function, a very simple function. In this case, it's a line. And lines have two variables, m plus n. Okay, and in this case, in order to feed the variables, we use a simple formula that can be implemented in Python, for example. Okay, here we have the theory, quite a lot of theory, and in the end we have a formula of how the linear regression is computed and how this is done iteratively, which is something similar to what will happen for deep learning networks. We will have some data and we will want to fit a model. In the case of linear regression, this model, this function that we want to fit to the data is very simple. It only has two variables. It's just a line. With deep learning networks, we will do the same thing, but the function that we have here, the deep learning network, will be a lot more complex. It will have easily millions of parameters, and it will have different nodes that will do different things and be connected in different ways, and this is just a conceptual thing, okay? Look that I even painted different colors to show that the nodes are grouped in something called layers, and these deep learning networks are called deep because they will have lots of layers, many more layers than classical artificial intelligence networks used to have. Remember, artificial neural networks are not new. For example, the perceptron shown here had one layer, but deep learning networks work in a similar way but have many more layers. And the idea is this, that I will have a function with many parameters, and this function will be flexible, and there is something called the universal approximation theorem that basically states that this function is infinitely adaptable. So deep learning networks represent functions with many variables that we can fit to potentially any type of data. Okay, that sounds very cool. That probably just means that they are very general. And the fact that they can theoretically be fit to any type of data doesn't mean that they will fit well to any type of data, or that it will be computable in any reasonable amount of time. It just means that they are very general. To sum up, basically we'll have some input, and in our case, for this course, our input will usually, I think, always be images. Okay, and images will be matrices of pixels. So I'll have basically a long list sorted in a certain way of, for example, if I have color images, RGB values. Then I will pass some of the images through my deep learning network, and I will change all of these many variables that my deep learning network, that my function has. I will adapt my deep learning network to the input data of my problem. That is called training the deep learning network. This fitting the model using some of my input data, some of my images, along with the correct answer that I want to get is called fitting the model, and that's the way that I'm going to use deep learning networks. I'm going to have some data with some answers grouped together. This is going to be called the training data. I'm going to use this training data to change the variables of my deep learning network to get the output that I want. In this case, for example, I want to solve the problem of identifying, of classifying sick trees, healthy trees, and dead trees. And I will give my deep learning network lots of examples of the three classes, sick, dead, and healthy. And then I will use that to adapt, to fine-tune, to set all of the parameters of this infinitely adaptable function to my output. Okay? To sum up, neural networks are functions. They have lots of variables, so they can be adapted to solve any type of problems. And I will always have my input data along with the answers that I want for the problem, and I will use those to train, to fine-tune my deep learning network. Okay, that will hopefully result in a function with the variables very nicely fine-tuned, so that when now I take some other data that I will probably call testing data, and I just give the data to the network without giving it the answer, it will also output the right answer. We will see lots more about this. So the first factor that resulted in this emergence of deep learning was artificial neural networks that now suddenly became deeper. How come they did become deeper? How come they were able to have many more layers? Well, thanks to a couple of interesting technical evolutions. First, convolutions, and second, the gradient descent optimizer. Okay, and those are two very technical concepts that I will not get into, but I will just say, I will not get into them too much, but I will just say that these are also not particularly new. For example, in this paper from 1998 by LeCun, there were already presence of gradient descent and of convolutions. 1998, so 18 years before AlphaGo. Many of the ideas of deep learning networks were already in this 2006 paper by Hinton and Osindirante. I will just give a very brief intuition of what these convolutional neural networks, what these convolutions mean. And I'm going to do it using the page from this Stanford course. The course is an in-person course, but at Stanford University, but these people are so nice that they have the lectures, the material for the lectures online and publicly available, and they have some very, very clear explanations of what deep learning is and how deep learning networks work. And I just wanted to show you this figure, which I think is a very nice explanation of what convolutions are. Basically, before deep learning networks, whenever I had one of the nodes in my deep learning network, I said before that here there are lots of different nodes that do different things. I didn't say that some of them are linear and some of them are non-linear, which is very cool because that allows me to model many more things. And these nodes do different things, and before deep learning, the size of that node, of those nodes, would be the same size as my data. So if I had data like this corresponding to an image or something, my nodes would be the same size. That was the age of fully connected neural networks. And well, these matrices representing images here are very small, but before I have shown one that was already quite a lot bigger, and even this one is just a patch, and we will often work with pictures that have many, many more pixels and that are much, much bigger. Okay, so basically, whenever we had a node, we needed lots and lots and lots of numbers that needed to be fine-tuned in that training step that I mentioned before. The thing with convolutions that was introduced already in 1989 1998 in these projects by LeCun, was that instead of having one node of the same size of the input, what we had were one or more small nodes, for example 3 times 3, that were moved over the input, as we are seeing here. Okay, they were multiplied times the input, and then a smaller result was produced. In this case, we have 3 of these convolutional filters. They are called filters, and each of them, when applied to our original image, is giving a result. Okay, sorry, we have 2, 1, and 2 3 by 3 by 3 filters. Okay, so when I multiply this matrix here, I get one number, and when I multiply this matrix here, I get another and another, and that gives me one of the numbers of the result, and whenever I move it, I get another one and another one and another one, and when I do the same for the second column, I get another one. Okay, you can read that with some more detail and somewhat better than I'm explaining it now, but the point is that instead of having very huge nodes at every point of in my network, I started having smaller things, and these smaller things help me summarize and decrease the amount of variables that I needed to update in my neural network. And probably people thought that that would decrease the performance of the networks, but the point is that it didn't. It allowed for networks with more nodes, and in particular more layers, and the performance of those networks was better than that of the original fully connected networks. Also, because of using gradient descent optimizer, which is an optimization system, an optimization method that's very flexible, some problems that had happened before with deep neural networks could be avoided. So these two technical innovations allowed for those deeper neural networks that had better performance than previously existing ones. And the third step was GPUs. GPUs are graphics processing units, and here you have a photo of one of the chips used, and these are the 3 deep learning capable GPU units in my office computer. These guys can make lots and lots and lots of simple computations like we need in deep learning networks. These are just matrix multiplication, so a lot of sums and multiplications and additions. Okay, so these GPU boards, these graphic cards, can be used to do those type of calculations extremely fast. Okay, that's also used, for example, for video games, which also use these cards, but they are they come in very handy for deep learning calculations. This allowed for even more layers in this new type of, let's say, somewhat lightweight convolutional neural networks. Finally, when we coupled it with data, we started having applications that could process lots and lots and lots of data, and data was suddenly available in larger quantities, and we could tackle more and more ambitious problems. When in the 80s and 90s those expert systems required lots and lots of experts annotating huge amounts of data, and that data was very difficult to access, and then it could not all be processed because the deep learning networks would have, the fully connected networks that existed there would have needed lots and lots of time to connect them, and their performance was not so great. So extremely good data was needed, and the right amount, and it took a long time to produce an expert system that did something interesting, suddenly all of those restrictions are somewhat relaxed. Now we have lots more data that can be processed super fast, and we don't really need such good annotations because these networks can adapt themselves to data much, much better. And that resulted in deep learning, this AI flavor, now being able to do some of the things that AI already did, but much, much better. And that's what produced all of those milestones. ImageNet competition, AlphaGo, we will see more of them. Many of the properties that had already been described for artificial intelligence suddenly worked. And I don't mean that they were lies before, but where things were very difficult to attain and needed lots and lots of years, suddenly deep learning could be used as a black box in many situations where data was fed and pretty amazing results were produced. And that's why deep learning became extremely popular in many research areas. It took over many, many research areas. And that's why we are speaking about this AI thing nowadays, and we are in this new age of AI boom. Okay? In the next couple of videos, I want to speak about two of these things that suddenly deep learning was able to do much, much better. One of them is called reinforcement learning, and the other is transfer learning.